Consider the following chemical equation where coefficients are represented by the letters W, X, Y, and Z. W Al2O3 plus X H2SO4 yields Y Al2SO4 3 plus Z H2O. If W equals 1, then which of these is true? A. Y equals 2, B. Z equals 3, or C. X equals 6. In a chemical equation, the number of atoms must be the same on both sides of the arrow for each element. To count atoms, we simply multiply the coefficient by the subscript. Let's set up a table that will allow us to relate the values of the coefficients W, X, Y, and Z. We find aluminum and aluminum oxide on the left. The coefficient of aluminum oxide is W, and the subscript of aluminum and aluminum oxide is 2. Therefore, the number of aluminum atoms on the left is equal to W times 2, or 2W. On the right-hand side, we see that the aluminum is found in aluminum sulfate. The coefficient of aluminum sulfate is Y, and the subscript of aluminum in aluminum sulfate is 2. Therefore, the number of aluminum atoms on the right is equal to Y times 2, or 2Y. Let's take a look at oxygen. We find it in both aluminum oxide and sulfuric acid on the left side. So the total number of oxygen atoms on the left side is equal to 3W plus 4X. The 3W comes from aluminum oxide. The coefficient of aluminum oxide is W, and the subscript of oxygen in aluminum oxide is 3. Similarly, the 4X comes from sulfuric acid. The coefficient of sulfuric acid is X, and the subscript of oxygen in sulfuric acid is 4. On the right-hand side, the number of oxygen atoms is 12Y plus Z. The 12Y comes from aluminum sulfate. The coefficient of aluminum sulfate is Y, and the total subscript of oxygen in aluminum sulfate is 12. There are 3 sulfates in aluminum sulfate, and there are 4 oxygen atoms in each sulfate. 3 times 4 equals 12. You should be able to derive the formulas for the rest of the table. Let's see what happens if we assign a value of 1 to W. So 2W equals 2 times 1, or 2. From the table, we can see that for aluminum to be balanced, 2W must be equal to 2Y. Therefore, 2Y must be also equal to 2. If 2Y equals 2, then Y must be equal to 1. Choice A is wrong. If W equals 1, then Y equals 1, not 2. Okay, at this point we know W and Y are both equal to 1. What else can we determine? Here, the number of sulfur atoms on the right is 3Y. We know that Y is equal to 1, so 3Y is equal to 3. In order for a chemical equation to be balanced, the number of sulfur atoms on the left must equal the number of sulfur atoms on the right. The number on the left is X. Therefore, X must be equal to 3. Therefore, choice C is also wrong. If W equals 1, then X equals 3, not 6. The correct answer must be choice B. Let's verify that Z is, in fact, equal to 3. Let's see what else can we identify in the table. We can see that the number of hydrogen atoms on the left is 2X. We already know that X is equal to 3. Therefore, 2X is equal to 2 times 3, or 6. In order for the chemical equation to be balanced, the number of hydrogen atoms on the right must be equal to 6. In other words, 2Z must be equal to 6. If 2 times z is equal to 6, then z itself must be equal to 3. Thus, the correct answer is B. If W is equal to 1, then Z is equal to 3. Let's verify that oxygen is also balanced. The number of oxygen atoms on the left is 15. 3W plus 4X is equal to 3 times 1 plus 4 times 3, or 15. The number of oxygen atoms on the right is also 15. 12y plus z is equal to 12 times 1 plus 3, or 15. So here's our chemical equation. The coefficients W, X, Y, and Z are 1, 3, 1, and 3. Note that this is just one way of balancing the equation. We can multiply all the coefficients by the same number and get another set of valid coefficients. For example, if we multiply all our coefficients by 2, instead of 1, 3, 1, and 3, we get 2, 6, 2, and 6. This is also a balanced equation. Or, if we multiply all the coefficients by 3, we get coefficients of 3, 9, 3, and 9. This is also a balanced equation. We can even use fraction coefficients. For example, we can multiply all the coefficients by 1/2. We get coefficients of 1/2, 3/2, 1/2, and 3/2. This is also a balanced chemical equation. We can assume any value for any one of the coefficients. Then we can figure out all of the other coefficients. It is, of course, convenient to deal with the smallest whole numbers. So that's what we did here.